Next we're going to look at question number 59 on page 7. It comes from chapter 4 of the textbook, Motion in Space. The question reads, Earth orbits once around the Sun every 365 and 1/4 days at an average radius of 1.5 times 10 to the 11th meters. Earth's mass is 6 times 10 to the 24th kilograms. A. How many seconds does it take Earth to orbit the Sun? B. What distance does Earth travel in 1 year? C. What is the Earth's average centripetal acceleration? And D. What is the average force that the Sun exerts on the Earth? Okay, so we're asked to find how many seconds does the Earth take to travel around the Sun. So T in seconds. Say T orbit in seconds. What distance does the Earth travel in 1 year? So the distance of one orbit. What is the Earth's average centripetal acceleration? And the force, the centripetal force. Okay. Given is time equals 365.25 days. That's the time of one orbit. Mass of the Earth is, let's say 5. That's 5 times 6. Sorry, times 10 to the 24th. Kilograms. And the average radius is 1.5 times 10 to the 11th meters. Oh, ready? But I forgot it. 1.5. That's the orbital radius. Alright. And so equations. Well, to find the orbital time, that's just a conversion from days to time. The distance of orbit, well, the distance of orbit is going to be the circumference of the circle, whose radius is the orbital radius. Then circumference of the circle is, so the orbital distance is 2 pi r. Circumference of the circle. The acceleration, we're going to find that, centripetal acceleration, by v squared over r. And how do we find the velocity? Well, the velocity is the distance traveled, so the orbital distance divided by the orbital time. This is in meters per, that's why we're asking us to find it in seconds, meters per second. Find the velocity first, then we can use that to find acceleration, and then the force is mass times acceleration. So let's first, so the equations. Let's first find this, do this conversion. So 365.25 days. Okay, so 1 day is equivalent to 24 hours. 1 hour is equivalent to 3,600 seconds. How do you get 3,600? Well, 60 minutes in an hour, 60 minutes in a second. 60 times 60 is 3,600. Alright, so take 365.25 times 24 times 3,600. I'm going to just write this right here. Let's go 1.6 times 10 to the 1, 2, 3, 4, 5, 6, 7 seconds. It's a lot of seconds in a year, right? Which we would expect. A lot of seconds in a year. So now the orbital distance. So the distance is 2 pi r, okay, which is 2 times pi times 1.5 times 10 to the 11th. Alright. So 1.5 times 2 times 3.14 gives me 9.42. That's what this is. And then times 10 to the 11th meters. I can leave it times 10 to the 11th because this is not, there's still only one digit left of the decimal place. This came out to 10, and I have to write it as 1.0 times 10 to the 12th. Alright, but if it's 9, it's fine. So orbital distance is 9.42 times 10 to the 11th meters. Right? That's how far it travels. That's the circumference of the circle. So now we can find the velocity, right? The speed is the orbital distance divided by the orbital time. 9.42 times 10 to the 11th meters divided by 3.16 times 10 to the 7th seconds. So we're doing this division first. 9.42 divided by 3.16. I get 2.98 times 10 to the 11 minus 7 is 4. So 4 meters per second. Alright, that is our orbital speed. That's how fast it's traveling on average. So now we can use that to find the centripetal acceleration. 2.98 times 10 to the 4th meters per second squared divided by our orbital radius, 1.5 times 10 to the 11th meters. Alright, so 2.98. So use it times 10 to the scientific notation calculator. There should be like an EE button on your calculator, a capital. I'm trying to find it on this one. Capital EE. You hit that, and you get a capital E on your calculator. That E stands for times 10 to the. And so I'd write 2.98 E4. And I want to square that. I'm going to divide it by 1.5 times 10 to the 11. And I get 0.00592 meters per second squared. It's a small acceleration. So I come over here. I can rewrite that as acceleration is 5.92 times 10 to the negative 3 meters per second squared. And the force is on the mass times acceleration, which is 1.6 times 10 to 24 kilograms times 5.92 times 10 to the negative 3rd meters per second squared. So I'm multiplying acceleration by 6 times 10 to the 24, and I get force equals 3.55 times 10 to the 22 newtons. It's a large force. Large force generates a small acceleration. Right? Why? Well, the Earth is very massive, right? So a large force still generates a small acceleration because because it's so massive. Now, the acceleration is small, but if you think about it, from every day, from day to day, the orbital path of the Earth it's very large, right? And so the change in direction that the Earth has every second is minuscule, right? So remember, this is the change in direction of the Earth's velocity every second, right? How many meters per second per second? So it's minuscule, right? Because it's just a slow, gradual turn as it goes around the sun. The turning is gradual, right? It's very gradual, and so it makes sense that the acceleration would be small, especially in units of meters per second squared. If it was maybe kilometers per hour squared or kilometers per day squared, it might be a more substantial number because there's more of a change in its direction, right? Its direction changes by 90 degrees in 6 months, right? It changes by 180 degrees, no, sorry. It changes by 90 degrees in a quarter of a year, 3 months. It's traveling this way, 3 months later it's traveling this way, 6 months later it's traveling this way. So its velocity changes 180 degrees in 6 months, right? But in 1 second, its velocity barely changes direction as it goes around the sun. So that's actually, if we think about it, it seems like pretty reasonable. And that's a large force, right? It's a large force, which, yeah, the whole planet in orbit, I guess you need a large force.